few things that I forgot to mention. I updated the slides. You had before, a few hours ago, I don't remember exactly when, but you had 2 different pack of slides for this topic. Now you have only one, slightly updated. But if you downloaded the old ones, just download the new ones. And I'm recording the lectures, okay? So I will put the lectures on YouTube probably, and I will post the link somewhere in the Moodle site of the course. So don't panic if you can't attend both lessons or whatever. You obviously can do projects on this topic. This is part of the exam. Before embarking, let's say, in a project on this topic, maybe send me an email to check if the project is fine, okay? The project must be relatively small because its weight in the final exam is not so big, so you cannot work 3 months on the distributed artificial intelligence project unless you have a personal interest or you want to work on a thesis, an internship, whatever. So if you want to give this exam on this topic, get in touch with me so we can arrange a well-defined project that you can reasonably carry out in a reasonable amount of time. So as I said, up to now we defined half of the problem, the abstract formalization of the real-world problem we want to deal with. Now we need an abstract formalization of the kind of solution. Are there any properties I want to embed into my solution? Again, in single agent reinforcement learning, there is no question. We always maximize the expected return. There is only one expected return in the whole environment. Let's maximize it. In multi-agent reinforcement learning, it is not so easy. Okay? A solution concept in the definition of a multi-agent reinforcement learning problem is defining a set of properties that a solution must provide. If you remember, we said that what actually does matter in a multi-agent environment is not the individual policies of all the agents, but the joint policy. The policy that basically is the result of the concatenation of all the agent's actions. Okay? Keep in mind that each agent can have different policies. If they are learning, they can learn with a different learning algorithms. They can learn with the same algorithm but with different hyperparameters. They can learn with the same algorithm, same hyperparameters, but they have different observations. They maybe have different actions. So they can converge to different policies. So the joint action is simply the concatenation of all the agent actions. The kind of additional properties we want for our policy is can be basically anything that has to do with how do we want the expected returns to be distributed amongst the population of learning agents. Do we want that all the agents on average have more or less the same expected return? Well, our objective could be to minimize the variance of expected return. Do we only care to get to the goal? So we only care that at least one agent gets to the optimal policy. Who cares about the other? That's another thing. We want to maximize the expected return of at least one agent. So you can formulate this goal, this solution concept, in different ways. And we will mention a few. Some are here only as a mention. We won't delve into details. Some we will analyze a bit better. But some of these, I think you should be already familiar, for instance, with the concept of Nash equilibrium and maybe even Pareto optimal policies. So a joint policies, we already depicted it, okay? So it is the joint action is the concatenation of all the actions at a given time step, at a given decision point in the environment. The joint policy is what? The output of a learning algorithms that has the goal of choosing the best action for each agent. That's the joint policy. So, a policy that dictates what each agent should do. Most of the solution concepts that have been formalized to characterize the solution are built upon this very basic notion of best response. Given a set of agents, let's focus on one agent and call it I, the ego agent. All the other policies are identified by pi minus I. So these are the policies, the action policies of all the other agents. Okay? What is a policy? A sequence of decisions, a sequence of actions. You can easily imagine, I know that it may be hard to visualize concretely what is a policy, but it is very simple. You can visualize a policy as a decision tree, as a sequence of if then else statements. Okay, that's a policy. Given a state, I chose an action. The best response policy of the agent E, the policy of agent I, is called a best response policy if it is the policy that maximizes the expected return of that agent, the ego agent, while playing against those other policies fixed. Okay? Those policies cannot change. They are assumed to be fixed. Okay? So my best response is a policy that basically reacts to what others are doing, okay, in the best possible way. How best is measured according to the expected return. Okay? Such best response may be not unique. Okay? There may be multiple best response policies, even having fixed policies. Okay? Because multiple actions may lead to the same maximum expected return. Let me check one thing. This is tic-tac-toe. Let me check one other thing if I did an example. Otherwise I will do it. Okay, no. Okay, so I can do the example. So let's go back. I don't know why. Okay, now it's working apparently. Yes. For instance, if you're playing rock, paper, scissors, there are it is a very special case, only 2 agents, okay, but just to make it clear, this part. If you are playing rock, paper, scissors, there are multiple best response policies for me. I mean, every symbol, rock, paper, or scissors, can be a best policy, a best response policy, okay? Because I have exactly the same chance, 1/3 of a chance of winning, okay? So I have actually 3 policies that have the same actual best response, okay? That's an example. So let's try to understand better what this best response is. Again, in the specific case of 2 agents and a zero-sum game, so a game played by only 2 agents, fully competitive. If I win, you lose. Rock, paper, scissors, tic-tac-toe, card games in general, okay, whatever. Here, there is a very easy, special instance of best response that is called the minimax solution. That is also a solution algorithm, actually. The policy of one agent I is optimized against the worst case. That is, against an agent J that aims at minimizing the ego agent expected return. That's the worst case. I have an agent whose only purpose, an opponent, this is a competitive game, I have an opponent whose only purpose in life is not making me win, not making me achieve my goal, not letting me get to the reward. Okay? So the minimax is the policy of one agent that is optimized against an opponent that is trying instead to minimize my expected return. My goal is to maximize the expected return. My opponent's goal is to minimize my expected return. That's why it's called minimax. Every two-agent zero-sum game has a minimax solution, and this holds also for zero-sum stochastic games. Simply the demonstration, the proof is more complex. If there is more than one minimax policy, that could be the case. Okay. The nice property is that they all yield the same expected return, which means I don't need to select. I don't care. If I have multiple minimax policies, just pick one. Okay? They entail all the same expected return. Let's see if we can delve a bit deeper into this minimax concept. I have no idea what this is. I'm not connected, probably. Let me check if we can on the fly. Seems so. So let's mute the thing. You don't see it yet, but you now see it. Okay, so for instance, this is again this is not a matrix game like rock paper scissors because we have multiple states, but it is a zero-sum game and two players, so minimax is fine. What is the concept of minimax? We have again two agents, one is I, one is J. Sometimes it's called adversarial instead of competitive game. Again, some terminology issues. One agent has the objective of doing 3 crosses and the other 3 circles. So obviously they are competing against each other. Let's pause. We are not reading what's in the video, but what does it mean to play in the worst case scenario? Is there really a non-worst case scenario? For sure. I could play an opponent, a toddler, who is randomly placing the symbols on the board. Okay? So the worst case opponent means that our opponent is also trying to win the game. He's not randomly putting the circles of the crosses. Okay, so that's what it means to play against an adversarial opponent, against the worst case. So minimax is an actual algorithm that tries to look into the terminal states. What are the terminal states? The states in which the game is over. Nobody won, player X won, player circle won. Okay? These are examples of a terminal state. Okay? There may be many terminal states, obviously, because you can do 3 crosses horizontally, vertically, diagonally, whatever. So, whatever the terminal state, you can easily associate a value to the terminal state that is the payoff matrix of both agents, actually. Because since the game is zero-sum, if +1 is for the blue agent, then and -1 is from the perspective of the blue agent, the payoff matrix of the yellow agent is simply the opposite. -1 here, +1 here. Okay? So, both agents want to maximize their own expected return. But from the perspective of the other agent, these agents are minimizing the opponent's expected return. A zero-sum game. So, How does minimax work? Which again is the name of a solution concept. So the minimax solution is a solution that is the best response against the worst case. It is also the name of an algorithm, obviously. So how does the algorithm works? And this is not a learning algorithm. It's like dynamic programming. You can compute this in this sort of game. So let's assume this is the turn of the yellow player, which I think is the min player. So the negative of the reward. It is playing circles. So the agent simply looks at the board at the state of the game and builds a tree. How? By simply trying to imagine every possible action. Okay? What if I put a circle here? What if I put a circle here? Is this a terminal state? If this is a terminal state, I can readily choose the best action for me. Did I win? Did it end in a draw? Did I lose? If I can, I chose the action that makes me win. If I can't, I chose the action that makes me draw. If I can't, I lost. If this is not a terminal state, you simply iterate. Okay, assuming that this is the new state, where can I put another, where my opponent can put its own symbol? By doing this iteratively, you actually build a tree of the possible game states and all of the actions that lead you to that game state. Okay, now how can I choose how to play? Well, simple, navigate the tree backwards. Start from the leaves that gives you the maximum reward, and backward choose that actions. Okay, so now, if I remember well, we should see this sort of explosion and navigation of the tree. Let me check. Exactly, here. So this is a sort of pseudocode of the algorithm. And as you can see, basically, the two players estimate in the exact opposite the game state. So how do the game proceeds? In this way. Okay? The minimax algorithms that we sketched recursively enables agents to look ahead into how the game will go. Any of you that played any kind of strategic game, okay, more or less reasons in this way. In chess, you do reason in this way, okay? So, yellow agent in this case is reasoning about, no, in this case, sorry, the blue agent is reasoning, okay, what can the other agent do? Okay, if the other agent does this, I can do this. Okay, so every agent in turn expand this tree until they find the best policy that they can proceed to exploit. This is called, obviously, a game tree, okay? Which is basically the explosion of all the kind of situations you can find in the game. Chess is the same. Simply the game tree is extremely huge in chess. But the core idea is the same. Okay. So the minimax solution concept and the algorithm, but we do care most about the solution concept, is simply a solution concept that it is quite narrow, can be used only for two agents zero-sum games, but it is an example of a best response. Other two examples of solution concepts that are built upon the best response are the Nash equilibrium and the concept of Pareto optimality. Nash equilibrium means that this is an equilibrium because it is a property that holds between all the policies of all the agents. No agent can improve its own expected return by deviating from its policy. So let's try to do another action. Can I increase my expected return? If I am in a Nash equilibrium with the policies of other agents, the answer is no, you can't increase your expected return unless you change also the other agent's policy. So let's assume that the other agents keep playing the game as they are playing now. Can I improve my expected return? If our policies are in a Nash equilibrium, the answer is no. Each agent policy is the best response to every other agent. Every agent is basically trying to play against a worst case in which every other agent is playing to minimize its own expected return. In a sense, the Nash equilibrium is a sort of worst case scenario. Okay? I assume the worst possible scenario. Everybody is against me. Pareto optimality instead is slightly different. Obviously the things can be related, but it is not strictly an equilibrium in the sense that the Nash equilibrium is a property that relates all the policies. The Pareto optimality instead, it is not referred to a solution, but it is referred to a joint policy, so the concatenation of all the policies of the agent. So you can say that a joint policy is Pareto optimal if no other joint policy, or there is no other concatenation of agents' policies, that gives better return for somebody, at least one agent, could be more, without making somebody else worse. Okay? They may seem similar, but they are quite different. In fact, for instance, you can have a Pareto joint optimal policy that is also a Nash equilibrium, but if you have a Pareto joint optimal policy, knowing this alone doesn't tell you anything about the Nash equilibrium. So you can have a Pareto joint optimal policy that is not a Nash equilibrium. Because the Nash equilibrium doesn't tell us anything about the relationship between different policies. It only says that, assuming that other policy stays fixed, no agent can improve by deviating. Instead, the Pareto optimal policy tells us something between different policies. I am in a Pareto optimal joint policies if I cannot move one individual policy, making it better, without making another agent worse. So they are slightly different concepts. These are just examples, okay? Examples of additional properties you may want to achieve with your solution to a multi-agent reinforcement learning problem. I am creating a new reinforcement learning algorithm in a multi-agent setting, and I want this algorithm to find a Pareto optimal joint policy. This, for instance, this kind of concepts may seem a bit abstract, but the concept of Pareto optimal joint policy is largely used in economics. For instance, assume that you are the manager of a company, and you have to decide whether to invest your capital in buying, I don't know, more supplies, or in doing research about a new product, or in empowering your current equipment and machinery. The budget that you have is always the same. But you can distribute the budget in different ways among these three, let's say, investments. You are highly interested in finding the Pareto optimal distribution that entails you the highest return. Okay? So this kind of concept is quite practically relevant. We have seen basically one equilibrium. There may be more equilibrium concepts, okay? If you remember the slides about the challenges of multi-agent reinforcement learning, we mentioned this equilibrium selection issue. The fact that different agents may have different expected return. So how to define which is the agent that should be prioritized or whether the agent should be all the same. So one issue, even with computing this kind of equilibriums, is that they don't really tell you anything about the returns. I mean, being in a Nash equilibrium doesn't tell me anything about whether I can get a better return overall. I don't know, by summing the return of all the agents. That's not what Nash equilibrium is telling us. So, the only guarantee, for instance, for the Nash equilibrium is that the policies are the best response reciprocally. The Nash equilibrium doesn't guarantee that, for instance, the sum of the individual returns is the maximal one. No guarantees that there isn't a better expected return. The prisoner dilemma is a cornerstone example of this. So, the problem with these equilibria, that they may seem like desirable properties to have for a solution, and most of the time they are, but the problem is that we cannot rely exclusively on them blindly. Because in general, for instance, there may be multiple equilibria in a given game. And all, in general, each of these different equilibria, even multiple Nash equilibria there can be in a game, they can entail different expected returns. Either in the distribution of expected returns between agents, we care about that, but even in the global expected return. So they may be a desirable properties, but do not mistake an equilibria for an optimal expected return. That's not the case. Okay? This is called equilibrium selection issue because if you have multiple equilibria and every equilibria can in principle give you a different expected return, you must select which equilibria you do want your agent to converge to. But you do not always may control. They are learning from interactions, there may be random factors, probability distribution, so you should find a way, an algorithm that steers your agents toward the best equilibrium according to your own desiderata. Again, average of expected return, maximum of expected return, minimum of expected return. We may have a practical problem in which we want to guarantee that no agent has no return, basically. Okay. So again, now we know, we scratch the surface, obviously. We know how to formulate a multi-agent reinforcement learning problem. We know how to formulate a model of the environment, a model of the game the agents are playing. So some of you, for instance, made some questions. I want to model a traffic light, and I want to teach the traffic light to adjust the duration of the red, the green lights, and the directions of the red and the green lights. This is called phase, usually, in traffic terminology. I want to adjust them adaptively, not with fixed time interval, but by learning from traffic conditions. So I deploy a software controller that controls the traffic light that learns with reinforcement learning. Okay. What kind of problem is it? Is it a market decision process? Is it a POMDP? Defining the kind of problem may help you decide which algorithm is best suited. And then you should define what kind of solution do you want. Do I want a solution that maximizes expected return and the reward is measured with the average speed of vehicles? Fine. it may be the case that you have one big green wave of vehicles that never stop, never brake, and some vehicles that are endlessly stuck with a red light. You chose to maximize the expected return, the maximum expected return, for instance, the velocity, the speed. Okay, no, maybe it's better to try to maximize, to try to minimize the maximum waiting time. So I want to have a fair allocation. I don't want vehicles to get stuck in traffic forever, okay? So maybe my whole network will become a bit slower, but at least every vehicle gets the chance to cross the intersection. So as you can see, it is not so easy anymore to define the goal of your reinforcement learning. This is what we did with these two first with these two sections. Now finally, okay, we can start talking about, okay, fine, we know how to formulate a problem, we know which kind of solution do we want, how do we get to that solution? Okay, so learning is just a way to compute a solution to a problem. Instead of programming, dynamic programming, minimax algorithm, Monte Carlo tree search, whatever you can think of, you want to learn the solution. For whatever reason, okay? I don't care much about the reason. Obviously, in research, you do care about the reason. Reasons could be, it is too difficult to come up with a solution. Or the solution inevitably will be crafted, maybe it does a lot of, it exploits heavily a heuristic solution. So anytime I change the problem, I must change my solution. So I get tired, I get bored, I want to learn a solution, okay, stuff like that. So, reinforcement learning at its core is a way to compute a solution to a problem. That's it. What are the elements of this learning process? Some of them you already mentioned. The game, so the environment, and possibly also the interactions between agents. The goal, okay, what do we want to achieve? Some sort of optimal joint policy, depending on some sort of equilibrium or notion of optimality, like Pareto optimality. Obviously we need an algorithm, a learning algorithm. In supervised learning you have decision trees, upper vector machines, and whatnot. Here you have proximal policy optimization, co-learning, author critique, whatever. It is a function, basically, at some level of abstraction, that, given some data and the current decision-making policy, outputs a new policy. That's what a learning algorithm is in reinforcement learning. And you need data. Every data-driven learning process needs data. So in supervised learning, for instance, let's assume you are doing prediction. You don't really have the game, but your game is predicting a label. Your goal is optimizing some measure of accuracy, precision recall, F1 score, whatever you can think of. Your algorithm is support vector machines, KNN, I don't know what. And your data is a dataset. In reinforcement learning, you don't have a dataset, unless you're doing one thing that is called offline reinforcement learning that we don't care about here. Your data is a bit of peculiar with respect to all of the other machine learning paradigms, because the data is the data produced by the agent itself. It is not something that is given by somebody else already built. The data is the collection of, sometimes they are called trajectories, histories. The collection of states, actions, and rewards that are produced by the joint policy in multi-agent reinforcement learning. So you are building your dataset while you are learning. This is actually quite a peculiar difference with respect to supervised and unsupervised learning. How do we evaluate a learning process in reinforcement learning? Well, two families of approaches. We won't go into the details, but a strong form of evaluation will be to prove the convergence to any given desired solution. I can prove that my process converges to a Pareto optimal joint policy. A weaker family of approaches is I just show you then with more experience my agents get better at achieving returns. This is an empirical evaluation. Sometimes you do not even know beforehand what is the optimal policy. So you cannot really compare and find the difference between your expected return and the optimal one. So you just show this sort of learning curves. So our usual schema to sort out concepts. What is the game? Well, basically the game is everything. The agent plus possibly interactions between agents, possibly. Because for instance, in game theory, agents do not interact but for playing the game. They do not communicate information. What is the data? Observation and side rewards. Obviously the action. Each agent knows its own action. The algorithm, given the data and the current policy, outputs a new policy, which may be equal to the old one, if it's already optimal, or if we, for some reason, are trapped in a local optimum. Can be. And the goal is finding a joint policy plus something, some desired property over this joint policy. Simplest examples that come to mind, well, you can apply single agent reinforcement learning algorithms in a multi-agent setting. As simple as it is. Simply, from the point of view of each agent, every other agent is part of the environment. I mean, I don't recognize them. I don't care about what they do. I'm not playing best response. I'm learning based on my observations, based on my rewards, and I completely ignore the fact that there are other agents that are learning. On paper, this approach is a failure because we have no stationarity of the environment, no? The challenges that we originally mentioned. And for instance, Q-learning is a nice single agent algorithm because it has a proof of convergence. Given enough experience, enough data, enough time, Q-learning will converge to the optimal policy. Does this proof of convergence hold also in the case of a non-stationary environment? No. This doesn't mean that Q-learning cannot absolutely work in a multi-agent system. It just means that you lose the convergence guarantee. It can work, but you are not guaranteed that it will work. Anyway, that's the simplest case. Sorry for the... We can try to shut down the lights for a few minutes. The lecture is almost over, so... Okay. I thought they were front and rear, but they are not like this. Can you see something? No. Bad choice of colors. Okay, now you can see in this night atmosphere. This is the Q-learning agent. This is Python. I don't know if all of you are familiar with Python, but nevertheless, these are more or less 20 lines of code, okay? Not a program with billions of classes. This is the environment. This is where the agent and the environment interact. The environment takes a step. A decision has to be made. The action is what the agent decided to do. Based on this interaction, okay, the learner updates its own function. This is where the learning happens. These 1, 2, 3, 4, 5 lines of code, but just because they are formatted, are actually the implementation of the key learning update rule that you have in the slides. Okay? So, the two ingredients of any reinforcement learning, even multi-agent reinforcement learning process, are there. An agent that where is that blah 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 acts on the environment, collects a next state and a reward, and based on them learns how to adjust its own policy. Again, I mean, you have the full code implementation later in the slides. There is a link to the source code repository, but the whole thing is like a few tens of lines of code. Okay, nothing. You can write it in less than an hour. What you can do with this simple Q-learning, let's see if it works. You can do this. Simple game. You are this little, I don't know, to me it resembles a sort of a Christmas elf, but maybe it's just for the period. But this is this little guy has to reach the gift without falling into the holes. The starting position, the goal position, and the holes are always in the same position. So this is a very easy problem. And you do want to learn what is the optimal path. Okay, this is just a toy example. So obviously it doesn't make sense because everything is fixed. You can't compute the actual path, optimal path, but this is just an example. So at the start of learning, this is what the agent may do. If you remember what we said about reinforcement learning, is that essentially it is a trial and error process. The agent knows nothing about the environment, okay? Doesn't know what falling into a hole means. The agent only discovers that falling into a hole is bad when it gets a negative reward. The agent does not know that it has to get to the gift. It only discovers that when it gets a positive reward. Okay, so basically, from the standpoint of this little guy, he gets thrown into this environment and has no idea about what to do. So it starts doing random actions. Let's go left, let's go right, let's go straight, go back, go straight again. Sooner or later, this happens. Okay? More or less, for some reason, the guy decided that this is the optimal path. But as you can see, sometimes it doesn't really follow the optimal path, but goes back and forth, maybe performs a loop, stuff like that. But we can argue that the starting policy has considerably improved later thanks to learning. Okay? What is here? A convenient representation of the so-called Q values. They are peculiar of the Q-learning algorithm. What do they measure? The Q value is a numerical value, a scalar, like the reward, that the agent attributes to each state action pair, which means in this state, here it is convenient because the state actually maps nicely to the actual game environment. In this state, this tile of the environment, I can do action go up, action go left, action go down, action go right. Okay? Through learning, I assign a Q value to each of these actions in this state. Then I do the same in this state, 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 in every state. Okay? What do these numerical values mean? How worth it is to go down when I'm here? How worth it is to go up when I'm here? How worth measured in terms of if I go down, what is the return, long-term return that I can expect from here? Well, for sure it is better that staying here, that going up. Here the game arena is actually bounded, so if you try to go up, you stay there. So going down actually has a higher value than going up or left. Here, going right has a higher value than going left, down, or up. Here, sorry. Down, left, or up. Because here is the goal. The best value is going right. So, this is a nice depiction in which the arrow is the action with the highest Q value in that state. So in this state, the action with the highest Q value, so the best action, is going down. And the color is how confident the agent is that that's the best Q value. Which means, for instance, that how far it is that action, the Q value of that action, with respect to the other possible actions. For instance, you can see that here we can argue that going down should have more or less the same value as going right. Because since this is a completely discrete environment, here what does matter is not the Euclidean distance, but it's a Manhattan distance. So doing this is the same as doing this, is the same as doing this. Okay? There are many optimal policies that entails the same expected return. In fact, I can argue that this color is more or less here. Which means that in this state, if I could look at the Q table of the agent, action go down would have more or less half of the, let's say, total value in the all possible Q values. Going right, the other half. Going up and going left, almost zero. Okay? So this is a nice visualization actually of the many optimal policies that you can follow. In this case, the optimal policy, if we have a greedy agent that always chooses the best action, which is not the case because here there were loops, it means that the agent sometimes took a random action. The optimal policy for this agent is this: down, 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 right, down, down, right, right, down, right, 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 right. It is one of the many optimal policies. But a greedy agent, an agent that never performs a random choice, would always follow this path. Always. Obviously, this is a single agent scenario. Okay? You can play with it. There are a few requirements. Everything should work out of the box. If it's not the case, just send me an email. But what if we have a multi-agent environment? We will see in the next episode, okay? So, next Monday, I think, we will continue and actually conclude the lectures about reinforcement learning.